Hi, I'm going to talk through a problem that I've done with my physics class here, Cal State Dominguez Hills. This was for the calculus-based physics second semester. We call it Physics 132. It's a common course on any college campus. Really, the algebra and the problem I'm going to do is high school algebra level. And technically, this whole problem could be solved at that level, but it's conceptually a little bit weird. And I think some people had trouble with it because of that. Now, I actually had this problem on my first test this semester in spring 2026, and I had actually previously told the class that the geometric optics problem on the test might be the one that's conceptually difficult on the test. So here is the problem. It starts out completely basic. You got a converging lens, given focal length, an object, a given distance from it. I ask what distance the image is from the lens. I ask the magnification. I ask if the image is real or virtual. Should be very straightforward, and I think was for most people. But here's where it gets weird. I put a second lens into the system. It's a diverging lens with a given focal length, a rather long focal length compared to the first lens, and it's along the same axis and on a particular side. And I've got diagrams. I'm going to go through this whole thing. So I ask where compared to the new lens is the new image. And then I ask what the overall magnification for the two lens system and the final image, is it real or virtual? And I've got drawings that I made on paper, so I apologize, they're a little bit messy, but I used grid paper, so it's to scale. I also, at the end of this, I'll talk about some extensions of this problem if you're really interested in optics, how you could use it to understand more things. So there's my diagram for parts A and B, kind of standard way we do it. I've got my little arrow as an object. I've drawn the focal points of that converging lens, and I drew a little fat thing there for the converging lens, labeled my focal length, my distance to the object. And if you use different texts, where I use P and Q, distance to object, distance to image, you might use D subscript O and D subscript I. They're the same thing. The same equations, of course, apply. Okay, so in that first part, again, straightforward. Not going to actually do the algebra here because it's pretty simple if you're at this level. But 1 over P plus 1 over Q is 1 over F. Gives me Q di, if you use the other notation, of 3. The magnification, negative Q over P, is -2. So I've drawn my image here. I have drawn my image. I put a little orange on it just to accent it there. Twice as big, upside down, 3 meters or scaled meters away from the lens. I think everybody who attempted that problem got it or made some little silly error. Uh, again, very straightforward, I think. It's usually a good idea to trace a couple rays and just make sure you have confidence that you didn't forget something in the algebra or write some number incorrectly. I do not advocate trying to ray trace to get the exact answer because you have to be really careful with that. But I did draw a couple of rays in here. The other advantage of grid paper, I drew parallel to the axis, out through the focus, or in through the focus. And I actually missed the edge of where I drew the lens, but the lens could be arbitrarily long, of course, and then out parallel to the axis. And yeah, those cross in the right place. Not surprising. Not even particularly enlightening, I think. But now I put the second lens in. I've left out the original object. I did not draw it, and I'll go back and point to where it was again later, but I left it out on purpose now. Once I am on the right side of the converging lens, the original lens, I've got light rays that really are crossing where this real image from it was. That becomes the object for the new diverging lens. Now it's on the wrong side of the lens, which makes it a virtual object. You're used to having real objects viewed in diverging lenses making virtual images. This is a case where I've got a virtual object, and I did refer to that in class and talked through, without working the algebra, a couple of examples. Uh, a virtual object can give you a real image. I'm not saying you know that it has to be right away. I'm saying that it can, and I'm saying that we can calculate it. So where that virtual object is 2 meters away from this, right? Again, the virtue of using the grid paper here, I don't have to get the ruler out. And it's 2 meters on the wrong side, so it's a -2 for P, or DO. The focal length, I've only drawn the focal point on this side. Frankly, I should have moved everything over so I could draw the focal point on the other side because it's off the edge of the screen. But we've got P, we've got F, we have our equations. 1 over P plus 1 over Q equals 1 over F. And since P and F are both negative, I can get a positive Q, which I do. It's 4 meters. The new image is 4 meters in front of, that is on our view to the right of the diverging lens. The magnification due to the diverging lens, not what part D asks for, but due to the diverging lens, -Q over P gives me a +2 because P was negative. Thinking about tracing my light rays, I probably should have drawn the object in again, but the object head is there where the cursor is now, parallel going out through the focal point is through the middle of the diverging lens. When you go through the middle of the lens along the principal axis, you just keep going, which is how I got to that point. And yes, it looks like it gets to that point. The ray that went from from the tip through the focus comes out parallel to the axis. Again, it misses the edge of what I drew, but we don't know how wide the lens was. This one should go out from the focus, and it should be the focus on the left side. It's almost off the edge of the page. So it's going to come off at some angle like that. And yes, indeed, if you were careful, it does cross there. This gives me confidence that my calculation, my assertion that the object was virtual indeed makes sense. And I do have light rays coming through at that point. So overall, my magnification, I got magnified by the converging lens twice in size and inverted because of the minus sign. I got another factor of 2 from the diverging lens. So my overall magnification is -4. Light rays really are crossing there. So this is a real image. This is the solution to the whole problem as asked. Now I want to give a couple of extensions of what you might think about if you enjoy playing with the algebra or if you want to understand lens systems more. First thing I want to say is these kind of problems with geometric optics are reversible. So if I had an object where this final image was a real object, I would get a real image back where the original object was. Kind of interesting, isn't it? I could ask a question. It's a little bit harder algebraically, but no big deal really. What one lens system would make that set of object and image? And with a one lens, I don't know where the lens is, and I don't know what the focal length is, but I know the distance from the image to the object, and I know the overall magnification. So I know P plus Q, and I know -Q over P. So I can solve that for Q and P, and that will give me F. And then relative to those things, I know where that lens is. And it'll turn out that it's somewhere in this region in between the original converging lens and its focal point, I think right around here somewhere. And of course, the focal length won't be the same as either of those. Because what's really going on in this system, this compound lens system, is that the converging lens is bringing light rays together, and the diverging lens with a longer focal length, meaning a weaker lens, is making them diverge a little bit so they don't come together as soon. So, okay, that's just algebraically kind of interesting. When I think about it in this mode where that big object gives me a real image back here, this is sort of how a telephoto lens works. And think about it if I then, instead of mimicking this system, so what if I move that diverging lens a little in or out? Well, that would move this image in the problem given, or in the reverse problem, it would move at what distance, at what distance an object would be focused on to give you an image back here where the film or the CCD is in the camera. So working a little more algebra and playing around with the parameters here, and it really help you understand what goes on in a real telephoto lens. Of course, those are more complicated than just this pair and just that motion, but uh, it'll give you a lot of real understanding if you're interested in that kind of stuff. I'll leave it alone for now. I've solved the problem on the test and I've gone a lot farther than most of you really want to go with this. So bye for now.